So today we're going to talk about series and convergence. So last time we talked about sequences, and there's another thing called a series. So basically a series is when you add up all the terms in a sequence, right? So for example, a series is this. Notice that you're adding every single term to one another, where a sequence, you're just listing those items, all right? So let's go to example number 1 here. And then now it says, write the indicated parts of the sum S of n. Now, S of n stands for the sum. Okay, so first, S of 1, all that means to you is when you're doing this, you just want to know what the sum is. When you plug in, let's see, a 1 into the first term. So remember, you have this term right here. So you're going to plug in a 1 for n. So you have 1 over 2, 1 minus 1, which is 1 over 2 to the 0 power. 2 to the 0 power is 1, so all of this is going to be 1. Okay, now S of 2, you're going to add the previous term that we just found, which was 1. And then we're going to add up, we're going to plug in a 2 for n. So essentially you would have a 2 over 1 over 2 to the power of 2 minus 1. So that's going to be 1/2. So the answer to this one is 3/2, right? Now S of 3, you're going to add the two previous terms of this series, and then you're going to add the next one. Now then the next one, you would have a 3 minus 1 over 2 to the power of 3 minus 1, which is 1 over 2 squared, which is going to make that a 1/4. Okay, so S of n is basically asking you to predict what's going to happen, all right? So sometimes they might get a slightly different thing, but in this case, if I just keep adding 1/4 plus 1/8, and if I just keep going, eventually I would end up with the same thing that I started with basically the sum, all right, or the formula for the sum. Now, when we talk about this, okay, now notice that there's going to be a lot of different rules that some of you technically are supposed to be familiar with from pre-calc, but I know most of you have not covered that yet. So if the sequence of partial sum converges to S, all right, S being a sum, then the series converges, all right? So let's look at the next ones, because I feel like if you actually do some of the math, it kind of makes a little bit more sense instead of just reading the theorems and then trying to understand what those says, all right? So now we're going to talk about something called a geometric series. Now, notice that a geometric series has the following characteristics, right? You have some kind of constant, which they call A. Let me switch colors here for you so you're able to see that better. Well, they call A, and then you have some kind of ratio to the power of n minus 1. Okay, so now a geometric series with a ratio of r diverges if the absolute value of the rate is greater than or equal to 1. And I'm going to give you an example in just a second. If the rate is in between, if the absolute value of the rate is between 0 and 1, then the series is going to converge. Now remember, the converging means that you're approaching the same or a single value. Okay. All right, so let's go ahead and just go on to example number 2. It says, consider the infinite geometric series, and then you can kind of see that 8 plus 8 over 5 plus 8 over 25, and so on and so on. All right, so A of 1, well, A of 1, now remember, when they use the letter A in this case, all right, they're actually talking about the very first term that you have here. So A1 is going to be 8. Now, R is going to take a little bit of work perhaps on your part to figure out what that is, but all right, so think about it. A of 2 is 1 over 5. Okay, so A of 2 is 8 over 5. So R is going to be 1 over 5. And hopefully you can see when I write the explicit rule for A of n how I found that. All right, we can say, and your answer may vary a little bit here. We have the infinite sum. I say this is 8, and this is 1 over 5. I'm going to call this, and I wrote a number wrong here. I should have written a 1 there. I'm going to call this n minus 1. Now, you could have also written that as n is equal to 0, and instead of writing n minus 1, you could have just written, well, just n. All right, but I'm going to just proceed like what I have here. All right, so notice again that if I plug in a 2, for example, I'm supposed to get an 8 over 5. And you can see that I do. If I plug in a 3, that would give me a 1/5 squared, which will give me 1 over 25 times 8. That gives me the third term. Okay, and so on and so on. So now we're going to find the fourth partial sum. So what that means basically is we're going to add up the first 4 terms, which in this case, they have already written that for us. And by the way, you do have that key on your calculator. If you go to the math menu, I actually don't remember exactly which number that is, but it is on there. Okay. So if you add all those up, you get 1248 over 125. All right, now to find the infinite sum, okay, notice that you have this formula over here. Let's see. And obviously, if you had a calculator, you can probably guesstimate a little bit better what this would be, but we're going to use that formula. All right, so S of n can also be defined for a geometric series as a of 1 over, and this is kind of important here because we're going to use that extensively, 1 minus r. So a of 1 is 8 over 1 minus the rate, which in my case, r is 1/5, right? And if you do some of the math in there, let's see, that would give me 4/5. I think the answer is 10. And I don't have a calculator with me, but let's see. Yeah, that is 10. Okay, just wanted to make sure. All right, so now we want to find the limit of that sum that we just found, all right? So we can actually say the limit as n goes to infinity of 8, 1 over 5, n minus 1. It's really crappy infinity here. All right, and basically if you make this infinitely large, okay, then you're going to have of 1/5 to the infinite power. Well, that's going to make the number so small that's going to be approaching 0, which will make the whole limit 0. Okay, so now let's make sure we understand, all right, that the infinite sum and the limit of the sum is different. Okay, the infinite sum basically is going to tell you what you're approaching if you add all those numbers together. Okay, where the limit is a different thing. And we're going to do another example here that will possibly explain what I mean by that. And to me, guys, that was the hardest part to understand, all right, the difference between the two. So now in this one, they're asking us to find each of the following if possible. If not, okay, so we're going to try to find the sums of these, all right? So since I noticed that the first part, for example, is a geometric sum, okay, I can actually just use that formula I showed you where I used the first term, a of 1, which is 2 minus 1 minus r. Now this one, it's kind of hard to see that this is a geometric sum, but it is, all right? I could actually rewrite this as, let's see, 2n over 2. Think about it. 2n over 2 would be the same thing as 2 to the power of n minus 1 by those rules of exponents, right? When I divide, I can subtract the exponents. Times 1 over 5 to the n. Okay, so now let's see how I rewrote this. So I could actually rewrite this as 1/2 to the power, times 2n over 5 to the n, but I can write it like that instead, okay? So let's see. Let's see the first one works. Here, let me pause here for a second. I just want to make sure I'm not doing any of this wrong. All right, so continue on with what happened here, right? I just want to make sure that what I did was correct. So what I told you was still correct. I rewrote this as 2n over 2 times 1 over 5 to the n. Notice that I'm dealing with this, or I'm just trying to rewrite it in a way you can recognize it. Now, particularly in this one, I can rewrite this as 1 half 2 over 5 to the n. And really, the only reason I did that originally is so I can get this number, because at the beginning, I couldn't see how they got that. Right now, the 1/5 that I have up here, all right, remember the n starts at 1. All right, so if I plug in a 1 here, that would give me 2/5 times 1 half, which is going to give me 2 over 10, which is 1/5. Or you can just plug in a 1 for n and the original sum, and that should give you that. Okay, so now if you do all of the fractions and all of the math and all that stuff, that's just going to give you 10 over 3. Okay. Now on section B, I can split this up into two different fractions, if you will. Let's see. Now, in this one, we can say that R for both of these could be 1, right? Mainly because, and I'm talking about A. If I said R, I'm sorry, that's not what I meant. I mean, A is 1, the R over here is 4/5, and over here R should be 7/5. Now, the problem is that on this one, I know, according to the definition, that if R, which is this right here, if the absolute value of R, which is 7/5, if that's greater than 0, according to the definition of a geometric series, then the series is going to converge. Excuse me, diverge. Okay. All right. So let's go ahead and go to the next part. Now, the properties of infinite series. I think this is probably the most, probably the easiest to understand, because the work is very much like something we have done in the past. All right. So first, for a telescoping series, what we can do on here is we can use partial fraction decomposition, which I know sounds like a lot of fun, but you have done it before. All right, so what we can do first is we are going to split this up into, well, let me just write it. I'll shut up and you can just watch me do it for a second. You remember this? So basically, I'm multiplying both sides times the denominator. Okay, and then if you remember, what I'm going to do is I'm going to choose an n value, which, for example, if I pick a 0, right? Why am I picking a 0? Because if I plug in 0 for n, b will be completely eliminated, and I would end up with a times 0 plus 1, which is just a. So a is 1. And on this side, if I pick n is equal to -1, now why am I picking -1? Because that's going to eliminate the a value. Okay, so that would give me 1 is equal to b times -1, or b is equal to -1. So I can split the series, if you will, into two different type of series. I have one that would look like this, and I have another one that would look like this. And sometimes it's kind of hard to tell what's going to happen with these. So what you would do is just basically start plugging in numbers. All right. So if I plug in a 1 into this left sum, I would have 1. Minus if I plug in a 1 into this one, into the one on the right, I get a half. So again, I'm plugging in a 1 into both sums and subtracting them, right? Now we're going to add. So that's basically one term right there. Now I'm going to add the second term. So now we're going to plug in a 2 into each series. Let's see, minus 1/3. And if I add a 3 to this one, I would get a 1/3. If I add a 3 to this one, I get a 1/4. Minus 1/4. And hopefully you start to see what's happening, all right? And what's happening is that basically every term before is canceling the one after. So this one is canceling this, and the next one's going to be a plus 1/4. So essentially what we could have is we can have like, let's see, 1 minus n. Oh, well, I should be mathematically proper here. Plus dot, dot, dot. Minus 1 over n plus, 1 over n minus 1 minus n plus 1. So 1 over n plus 1 would be basically the last term on there. But my point here is that all of this other stuff would cancel, and you would end up with one, the first term, and the last term, basically. Okay? So this is the sum of the series. So to find the sum of the series, then you have to take the limit as n goes to infinity. And obviously, if you take the limit on this left side, if you take the limit of 1 over the limit as n goes to infinity of this would go to 0. And you would end up with 1. Okay? So could we have done that without doing that? Well, perhaps, but it definitely would have been harder, especially without a calculator, to know what the sum was approaching. All right. So basically what we're trying to do here is we're trying to find tricks, if you will, to figure out a way for us to find the sums of the series without having to literally write every single number. And trust me, if you would have plugged those numbers into the original one, which is this one, it would have taken you a lot longer to figure out that the sum was approaching 1. Okay. So now it says right here, given the sequence a of n is equal to 1 over n plus 1, explain the difference between the sequence and the series. And I think this is important, all right? So on the sequence, as I mentioned briefly at the beginning of the lesson, a of n, you're basically just plugging in one number at a time. But notice that I am not adding each term. Now, if I were to take the limit as n goes to infinity on this one, right, it would actually converge to 0. And this is really, really important, I think. So again, if I take the limit of just the sequence, which is what you see here, then sorry, I got lost. My wife took some kind of picture over there. Anyway, so the limit as n goes to infinity of the sequence goes to 0. Okay, so that's kind of important, where if I take the limit of the series, which is what I did on the last problem in example 4, right, of this, so this is the sum. And notice that on the sum looks very similar, but now instead of just writing the sequence down, I'm actually going to add every single term, and that's what we call this the sum. Okay. Now the sum is equals to 1, and that's sort of why, not sort of, this is why this are different, right? So for me, probably the hardest part is to understand why I was taking the limit and why I was getting different numbers when I would do that. But the thing to remember is that when you're trying to find the limit, or you're trying to find the sum, all right, you're basically taking the sum to infinity. All right, I have to do the steps that you saw me do to get to a place where I can actually plug that in. Okay. So it's not quite as easy as a sequence where all you have to do is just take the limit as n goes to infinity, for example. This one you have to do a little bit of work. All right. So this one's a little bit weird, but we're going to write a geometric series for the repeating decimal 0.05. All right. So 0.05 repeating. So you can probably agree with me that if I was just looking for 0.05, that would be the same thing as 5 over 100. 100 being 10 squared, right? So 5 over 100 is 0.05. Now, but remember, I'm not just looking for 0.05, okay? I want to actually find, basically I want to find it as a ratio of two integers. So now, oh, shoot. I don't know how that happened. All right. If I add 5 over 10 to the fourth, for example, now 5 over 10 to the fourth would be the same thing as, what is 0, I don't know, but it's 10,000. But my point is, you would actually get 0.0005. Okay, so notice that if you add those two together, I would get 0.0505. All right, and by that same logic, if I go for the next number, like 510 to the sixth power, that would be the same thing as me adding 0.000005. Okay, so that would give me the number 0.050505. Okay, so hopefully you can see by now, if I keep going in that sort of logic, if you will, then I would have the repeating decimal, right? So we can actually write this as a geometric series in the following way. Okay, we can say that if I go between 0 and infinity, I can say that A, my constant, is this, and the ratio I could have is 1 over 10 squared. And all right, so think about it. A, or A1, is the very first term that I have. Okay, and basically notice that what happens after that is that the power on the bottom just basically is multiplied by 2 every time. And how we do that is by basically multiplying the constant times 1 over 10 squared, because 10 squared times 10 squared is 10 to the fourth, right? And so on and so forth. So we can say that that's what it is, all right? So now to try to figure out the ratio as to integers, okay, we can actually use this formula that I showed you earlier. So we can say this is, now that we know this is the geometric series, we have 5 over 10 squared, which is the very first term, 1 minus 1 over 10 squared is the R. So this would be 5 over 100 over 99 over 100. And if you keep change and flip, you'll find out that the answer is 5 over 99. So 5 over 99 is 0.05 repeating. Kind of weird, huh? So let's see. Let me go back just a little bit. Yeah. Okay. All right. So now we're going to talk about the nth term test for divergence. Now, this gets kind of confusing, but And I did have to look at a couple of videos, and I will attach them on Google Classroom so you can see what I'm talking about. But essentially, all right, this part is not that useful. But what is useful is this one. All right. So what that says is if you take the limit of, let me make sure I use my words correctly. If you take the limit as n goes to infinity of a series, all right, and the limit is not zero, meaning it's anything other than zero, then you can actually assure, excuse me, let me reverse. Blah, 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 blah. If you take the limit of the sequence, okay, not the sum, but the sequence a of n, if it's not equal to zero, then the sum is definitely going to diverge. All right, so that's the important part because you can save yourself a whole lot of work instead of trying to figure out mathematically if something diverges by just using this test. All right, so here's the example that I'm talking about. Now, I'm not going to deal with the limit of the sum. I'm not going to do that. But what I can do is I can take the limit as n goes to infinity of an. An is just the sequence, right? Meaning I'm not going to deal with the sum right now. I just want to know what is the limit as n goes to infinity. Now, I feel sort of obligated to remind you how to do this. All right. Now, first, yes, you know that when you have something like this, you can use the horizontal asymptote rule. So I know my answer is going to be 1/5. But also, I want to remind you that if you have something more complicated, you can always take the term with the highest power and you're going to divide each term on the top and on the bottom by that term, by the term with the highest power. Sorry. Okay. And then you still take the limit as n goes to infinity. So, yeah, it's definitely a lot easier if you don't do this, but I notice that this right here goes to 0. Okay. So, more importantly, the answer is 1/5. So, again, I want to just remind you of that because not everything is going to follow those horizontal asymptote rules where if you use the method I just showed you where you just take the term with the highest power and divide every term by the term that has the highest power, that will work every time. All right, so anyway, this is 1/5. Okay, so is that 0? It's not 0, right? So because we know that 1/5 is not equal to 0, then I know that the sum, right, the sum is going to diverge. The sum is going to diverge. So, meaning the series is going to diverge. So, basically, if I take that sum all the way to infinity, it's not going to approach a single value. All right. Now, let's go to B, and we're going to do the same thing. All right. We're going to take the limit as n goes to infinity. And hopefully, this is something you can do relatively quickly. Now, this one, without further ado, this is 0. Now, notice that right here, this is kind of a confusing statement, right? It says that if the sum converges, that the limit of the sequence is 0. But the opposite is not true. I have this, but that doesn't mean that if I go this way, that's true. Not necessarily. So all you can say about a problem like this is that E may or may not converge. We don't know. That's the deal, all right? So this is why the first one is really not that useful, but the one that says that if you take the limit as of the sequence, if you take the limit as n goes to infinity of the sequence, if that's 0, then when actually we don't know if the sum is going to diverge or converge. We don't know. We don't know if it's going to converge. May or may not. Okay, so same thing on this one. If I take the limit as n goes to infinity of 1 over n, that's going to give me 0. But this one is actually, you may or may not converge, all right? But it turns out this is sort of a famous one. This is a harmonic motion sum that definitely will not converge, okay? But I'll send you a proof. I found a video of some guy doing it if you want to know. But as far as you know, right now, this may or may not converge. So the first part of that test, not that useful. The second part, very useful. Okay, let's go to the last part here. And we have formulas and term values for the nth term partial sums. Where am I? Oh, yeah. Okay. So in this part right here, right, notice that they give us the actual sum. This will actually give you the sum, okay? We want to write a rule for a of n, basically for the sequence. So this is how we're going to do it, all right? Now I want to give you a little what this would look like, all right? So just go there with me. You may not know why I'm doing this. To be honest, I don't even know why I'm doing this. Question myself all the time. But I mean, let's be real here. You're not even listening to this right now. So basically, if I keep going, I can write this as n minus 1 plus a to the n. Okay. So now I can say that this sum right here, right? This sum, let me change colors here. This sum right here, too much. I can call this sum n minus, get out of here, get out of here. There goes the third time. All right, so we can call this n minus 1. And I can call, let's make it purple for fun. Let's make it Granberry Pirate Purple. What a fabulous pirate. Anyways, S of N, on board. Okay, so what I'm going to say to you is that here's the idea, right? If I want to find out what A of N is, think about it. What I can do is I can write S of N. So let me write this in red here. I can say that A of N is equal to S of N, which is every term that you see all the way to an, and I can subtract S of n minus 1. Okay, so take a little time to make sure you understand that, because if you understand that, this becomes a whole lot easier. Again, A of n is when I add, S of n is every term added together, and S of n minus 1 is almost every term added together except for the very last one. Okay, so if I subtract those two, I will get just A of n by itself. All right, so now, assuming you agree with that, we can go ahead and do the homework. So, go ahead and do this problem. So A of n is S of n, which is defined for me. And S of n minus 1 is n minus 1. So I'm going to replace n with n minus 1. And really at that point, I'm just going to go ahead and do the math, get a single, I just want to get one single fraction here. So I'm going to find a common denominator. So this is going to be n squared plus 6n plus 8. This one's going to be n squared minus 6n minus 5. all of that over my common denominator of n plus 5, n plus 4. There's several things we're going to cancel, or maybe not several, but a few things we're going to cancel. And then when I end up with a minus 5, which is 3 over n plus 5, n plus 4. Okay. So this is equal to a of n. Okay. So let's go ahead and go to the last example. So this is very similar to what we have just done, but it's a little bit different. So notice that on this one, we're asked to find a of 6. All right, a of 6 stands for the last term on the sequence, okay? So we can write it like this. We can say that since what we know is the sum, that this right here gives us the sum, I can say that a1 plus a2 plus a3 plus a4 plus a5. I'm going to use basically the same logic I used in the last problem. So plus a6. We can agree that that's s of 6. Okay, so what we can do here, let me see what colors I used here. Okay. We know that S5 stands for the sum of the first 5 terms and S6 stands for the sum of the first 6 terms, right? So we can say that a of 6 would be equal to s of 6 minus s of 5. Now think about what that would be true, right? If I have s of 6 and I subtract s of 5, I basically delete the first 5 terms and I end up with the last one, right? Or in this case, a of 6. So now that we know that, we're able to just basically plug this in and pretty much game over after that. So let's see. I'm going to plug in that 6 for n here. Plug in a 5 here. And basically do all the math, blah, blah, blah. That would give you 13 over 14. Okay. So again, guys, not the most difficult. It is a little bit confusing, but I'm sure you'll have questions. I'll post part of the key. And if you have any questions, make sure and ask. All right. We'll see you next time.